So all of that was done in detail in lecture, so it should be pretty clear. So let me go to number 6. Now number 6 is interesting because number 6, now this is when you are going around in a circle, but the circle is horizontal. So when you are going around in a circle that is horizontal, then if this is the object that is going around, the free body diagram for that object is, of course, the normal force is here, you have the weight here, and then you have the frictional force here, as I said before. But the question that is being asked in this problem is, what is the total force exerted by the ground on the object? Well, that total force is the combination of these two forces. So the total force is going to have to be a vector that is going to point somewhere in this direction, and that will depend on the value of this normal force, which is equal to this weight, and the value of this one, which is equal to the centripetal acceleration times the mass. And so the information is given you to calculate that. I hope it's clear that the object is being pushed up by the ground with this force and also feels a frictional force. So the total force exerted on the car by the track is really this one over here. Let's go to number 7. Number 7 is circular orbits. So in circular orbits, we did the following. We said that if an object is circulating around a very heavy one, like the Earth around the Sun, or the Moon around the Earth, or a satellite around the Earth, this is the mass of the satellite. This is the distance between the centers. And this is, if the object is going around in uniform circular motion, this is what Newton's law tells you, from where you deduce that the velocity square of the object is the gravitational constant times the mass divided by the radius. Well, it's also solved in problem numbers 7 and 8. What happens is that the linear speed is in circular motion, so that is equal to the distance that you travel in one turn divided by the time that it takes to do one turn. So a square is this. So this is equal to that. That's how it was deduced in class, from where you conclude that the square of the period is 4 pi square divided by big G divided by the mass of the object that you are rotating about times the cube of the radius. This is third law of Kepler. So in problem 7 and 8, in problem 7, if you want to evaluate how fast we are going around the Earth, you have to evaluate this. And this is 2 pi over the period, and you know the period. If you now want to have two satellites, like in number 8, that are going around Jupiter, and one they give you the the period for one and with a certain radius, and then they give you another radius, and then you can calculate the period by taking the ratio between the two expressions. In number 9, remember you are going to have here one equation from one orbit and another equation from another orbit. When you take the ratio, the factor r who shows up there in the question is going to cancel out. And problem number 9 and problem number 10 are problems of the constant angular velocity. Constant angular velocity alpha, we deduced the equation this morning. So in the first case, if you push a merry-go-round from rest, and so you start pushing it and then you give it a final angular velocity, and you do that at a constant angular acceleration, you want to know what that acceleration is. So one way to know that is that if you know the final and you start from rest, then you will know the angular acceleration if you know the displacement that you did with the merry-go-round. And I remember that one revolution is 2 pi. In number 10 is a problem of reaching a certain angular speed from rest in a certain amount of time. Therefore, you can certainly calculate that number. And once you calculate this, you can calculate the total displacement. When you start from rest, the total displacement is just given by that. So I think that will do it, and it's time to stop it.